All right, so, okay. So now we're gonna try to again build a mathematical model of this problem. Okay, let's get started, please. All right, so this is a problem we have. You know, we are actually producing orange juices, different types of orange juices, using different types of oranges. And the question is basically how should we blend them? So how should we mix the oranges so that we actually produce orange juices and we meet certain production requirements, and we also have certain stock limitations as well. Okay, so we cannot use more than, for example, 100 kilograms of grade 1 oranges, more than 120 kilograms of grade 2, and so on and so forth. Okay, so again, we're going to start with the following. What are the decision variables? So once again, the question is basically, what are the factors that we can control in this problem? It's pretty much the same as the previous one, so I can control the following. How much grade 1 orange I'm going to use in the production of superior. How much grade 1 orange I'm going to use in the production of premium, and so on and so forth. Okay? So as a result, I'm going to define it in the following way. I'm going to denote by x sub si. So I have two indices. So this is number of kilograms of grade I orange used to produce superior orange juice. Okay? So XSI denotes number of kilograms of grade I orange. I can be 1, 2, or 3, used to produce superior orange juice. Then I'm going to define XPI in a similar way. So this is the number of kilograms of grade I orange used to produce, this time, premium orange juice. And finally, I'm going to define XRI to be the number of kilograms of grade I orange used to produce regular oranges. So once again, I need to specify that I can take the values of 1, 2, and 3. All right, so how many decision variables do I have? So I have 3 from the first set, 3 from the second one, and 3 from the last one. So if I add them up, I have 9 decision variables. And indeed, if you look at that picture, it's not too hard to see that there are a total of 9 arcs, 9 arrows, basically, right? All right, so now let's try to construct our model. Let me continue from here. So what is my objective? What is my goal in this problem? What am I trying to do? I want to maximize total profit, right? So how can I maximize total profit? Or what's the expression that expresses my total profit? Well, first of all, this is a maximization problem, right? So I'm maximizing my total profit. So as a result, I'm going to start with max. So let me first focus on the superior orange juice. So I'm going to denote, or I'm going to multiply the total number of liters of superior orange juice I'm going to produce by 1.5. Okay? So 1.5 is the profit per liter for superior orange juice. Now I need to figure out how much superior orange juice I'm going to produce. Okay? Well, so there's one problem. So here, this is the number of kilograms of grade I orange. Okay? Over here, I have the profit in terms of liters. So I cannot really multiply 1.5 with XSI, right? Okay? Well, let me just go back here. For each kilogram of grade 1 orange, I obtain 0.4 liters of orange juice, right? For each kilogram of grade 2 orange, I obtain 0.5 and 0.6 here, okay? So what am I controlling here? I can control the number of kilograms of oranges I'm going to use, okay? What I cannot control is how much juice I'm going to have. Okay? These are given to me. So as a result, what I need to do is I need to figure out, if I use this much orange in my production, how much output am I going to have? Okay? How much orange juice am I going to produce? Okay? All right, so let's figure out the sort of total number of liters of superior orange juice we're going to produce. Well, to produce superior orange juice, we can use grade 1 oranges, or grade 2 oranges, or grade 3 oranges. Okay? And if I use excess 1 of oranges in the production, okay, excess 1 kilograms of grade 1 oranges, how much juice am I going to have? Well, 0.4 times that, basically, right? So as a result, I need to actually sort of do the following. I'm going to multiply this by 0.4 times excess 1 plus, then I can also use grade 2 oranges. Okay? So for each kilogram of grade 2 orange, I get 0.5 liters of juice. So I have 0.5 times excess 2 plus, I'm going to have 0.6 times excess 3. Okay? So let's think about this a little again. So this is the total number of grade 1 oranges I'm going to use in the production of superior oranges. Okay? And if I use this many kilograms, then this is the total juice I'm going to get. Okay? Plus, this is the number of oranges, number of kilograms of grade 2 oranges I'm going to use. And if I use this many kilograms, then I'm going to get this much juice, basically. And finally, for grade 3 oranges. Okay? So the term in the parentheses, basically, is precisely the expression for the total number of liters of superior oranges I'm going to produce. Okay? And that I multiply by 1.5, which is the product per liter, profit per liter, rather. Is that clear? Okay? So this is the profit for superior orange juice. Now I need to compute this profit for premium orange juice. So I'm going to have 1.0 times. Now what's the expression for the total number of liters of premium orange juice I'm going to produce? So I'll just play the same game, right? So I have 0.4 times, this times I have XP1, right? Then I'm going to have 0.5 times XP2. Then I'm going to have 0.6 times XP3. So once again, the term in the parentheses is total production amount in terms of premium orange juice. Okay? And that I multiply by the profit. And finally, I'm going to have 0.75 times, I'll just do the same thing for regular oranges. Now, the question is the following. So, is this a valid objective function for an LP problem? Well, it doesn't look exactly in the format that we have seen, but it can easily be put into format that we have seen, right? So, if you just multiply 1.45 times 0.4, that's going to be the constant in terms of in front of x1. Then 1.5 times 0.5 would be the constant in front of xs2, and so on and so forth. Okay, so indeed, the objective function is in the form of an LP problem. Okay? So for each variable, you have a constant times variable, and then you add them up. Okay? All right, so this is our total profit. Now, what are the production requirements, or what are the constraints that I need to satisfy? Let me just go back here again. Let's start with this one. Okay? So we cannot use more oranges than we have in stock, and I need to express it as a constraint. So basically, total amount of, or total number of kilograms of grade 1 orange that I'm going to use cannot be more than 100. Okay? So how can I turn it into a constraint? Well, grade 1 oranges can be used in the production of superior, premium, and regular. So there are three sources that I can use, actually. Okay? So what I'm going to do is the following. So I'm going to have XS1 plus, what's the next term? XP1, exactly, plus XR1. So this cannot be more than 100. So this basically means that total number of kilograms of grade 1 orange I'm going to use cannot be more than what I have. Okay? All right, I'll just do the same thing for grade 2 oranges. by the same reasoning, grade 2 oranges can be used in production of superior, premium, and regular. Okay? What's the corresponding constraint? XS2 plus XP2 plus XR2 should be less than or equal to 150. So total number of kilograms of grade 2 orange I'm going to use cannot exceed 150. Okay? And finally, XS3 plus XP3 plus XR3. This cannot be more than 200. So if I go back here again, so now I just took care of all of these requirements, right? Okay? So once again, these are availability. So now let me focus on the daily production levels, okay, because it's easier to figure out. So I need to make sure that I'm going to produce at least this much, superior orange juice. How can I formulate as a constraint? So remember, this was the expression for the total amount of superior orange juice I'm going to produce. So I'll just copy that. So 0.4 times XS1 plus 0.5 times XS2 plus 0.6 times XS3. This should be at least as large as, because it's the minimum production level, 45. So this basically tells me that I need to produce at least 45 liters of superior orange juice. Then I need to produce at least 60 liters of premium orange juice. The expression for that is in the second term. So 0.4 times XP1 plus 0.5 times XP2 plus 0.6 times XP3 is at least 60. And finally 0.4 times XR1 plus 0.5 times XR2 plus 0.6 times XR3. This should be at least 100, right? So these constraints actually correspond to minimum production levels. Okay? Any questions so far? So now let's try to figure out the minimum average grade requirements. So how do you formulate that? Well, so now think of the following example. So suppose that I have one grade 1 orange and I have two grade 2 oranges. So what is the average grade I'm going to have from this combination? So it's going to be actually greater than 1.5. Why? Because I'm using more of better oranges, basically. Okay? The question is, how do I compute the average grade for such a combination? Well, here's what you do. So you use 1 of grade 1 orange. So 1 times 1. Plus, you use 2 of grade 2 oranges. So you have 2 times 2. So basically, this is nothing but I'm summing up all the grades that I use in my production. So I have grade 2 plus grade 2 plus grade 1. Right? If you add them up, you have 5, basically. Okay? How many oranges am I using? I'm using 3 of them, so I'm going to divide this by 3. Okay? So as a result, the average grade will be 5 over 3 with this combination. Okay? So essentially, then the way you compute this is as follows. You compute the total grades that you're going to use, total number of grades that you're going to use. Then you're going to divide it by the total number of oranges. Okay? And by doing so, you just get a weighted average, basically. Okay? So since you have more of better oranges, then the grade is actually 5.3 is like 1.66, which is larger than 1.5. Okay? If I use even more actual grade 2 oranges, then this grade will increase further. Does everybody see that? Okay? So if I use more of better oranges, then my grade will increase accordingly. All right, so now let me try to apply this idea to, for example, the superior oranges. Okay? So I want to make sure that the minimum average grade of superior oranges is 2.4. Okay? So in other words, I need to make sure that I'm going to come up with a combination of grade 1, grade 2, and grade 3 oranges so that the corresponding grade will be at least 2.4. Okay? So the question is the following. How can I formulate that as a constraint? Well, so let me go back to this picture again. So in the production of superior oranges, I use grade 1 oranges, I use grade 2 oranges, and I use grade 3 oranges, right? Okay? So So 1 times xs1 is the total number of grades coming from grade 1 oranges. Okay? 2 times xs2 is the total number of grades coming from grade 2 oranges. And 3 times xs3 is the total number of grades coming from grade 3 oranges. Okay? So essentially this is the total grade that I have. And I need to average this. So I need to divide it by xs1 plus xs2 plus xs3. Okay? So it's pretty much the same. I'm just generalizing this idea to xs1, xs2, and xs3. Okay? And I need to make sure that this ratio is at least 2.4. Okay? So once again, over here you have your total grades, and over here you have your total kilograms. So total grade divided by total kilograms should be at least 2.4. Okay? So this is precisely the average grade requirement. But there's one problem here. So this does not look like an LP constraint, right? Okay? In LP, we never actually allow the fraction of 2 constraints such as this one. Okay? So what can I do about that? Well, so if you multiply both sides by xs1 plus xs2 plus xs3, then this term will cancel, right? And this term will appear on the right-hand side. Okay? And then if I put everything on the left-hand side, now it's an LP constraint. Okay? Let me repeat that again. So in an LP problem, you can never have a constraint of this form. So this is not allowed. Okay? Why not? Because in an LP problem, we can only allow constraints of this form right here. So we can only have constraints of this form. So what I'm saying is basically the following. Despite the fact that that constraint is not of this form, it can be converted into this form exactly. Okay? So all I'm going to do is I'm going to multiply both terms by the denominator, both sides by the denominator. And if I do that, then xs1 plus xs2 plus xs3 will appear on the right-hand side. And then if I take everything to the left-hand side, then I have an LP constraint. Okay? And let's do that. So if I do that, I obtain the following. So xs1 plus 2xs2 plus 3xs3 minus 2.4 times xs1 plus xs2 plus xs3. So this should be greater than or equal to 0. So that constraint is essentially the same as that one, right? Okay? But the difference is that now this looks like an LP constraint. So this is a valid LP constraint. All right, so this was for the superior. So what about the premium? Well, I'll just play the same game. Basically, every time I see an S, I'm going to replace by P. Okay? So if I do that, I have xp1 plus 2xp2 plus 3xp3 minus, well, what's the correct number that I should use? 2.2 now, right? So I have 2.2 times the sum of all this, xp1 plus xp2 plus xp3. This should be greater than or equal to 0. And finally, I'll just do the same thing for regular. So xr1 plus 2xr2 plus 3xr3 minus, now I'm going to use 2.0. So that's the minimum average grade for regular. I have xr1 plus xr2 plus xr3. So I mean, one way to think about this minimum average grade requirement is just like your cumulative GPA, for instance, right? So you have some courses which are 4 credits, you have some courses which are 2 credits. So 4 credit courses actually affect your GPA more than 2 credit courses, okay? So you can think of the credits as your grades of your courses. Grades meaning the sort of, not the letter grades, but the quality of your course in some sense, okay? And then you multiply that by the numerical equivalent of your letter grade, and then you divide it by total number of courses, and essentially we do a similar thing here, okay? So it's essentially the same idea. So the cumulative GPA is just a weighted average of your grades, and a minimum average grade requirement is just a is just a weighted average of grade requirements, which is given right here. So before I move on, is this clear? So any questions about this? Yes.
Previous times we used our variables as liters, but in the minimum average we use kilograms. Why do we do that?
Okay, so the question is the following. In the previous problems we defined our decision variables in terms of liters, but here we define in terms of kilograms, and why do we do that? That's the question. Well, the question is basically, the reason is the following, because we can control how much orange we use, okay? And we use oranges in terms of kilograms, okay? So since I can control how much orange I can use, then I need to define my variables in terms of kilograms as well. So in other words, whether I use kilograms or liters depends on the problem, okay? So it depends on what I control. Okay, if the factor that I can control is given in terms of liters, then I'm going to use liters in my decision variable. If it's given in terms of kilograms, then I'm going to use kilograms in my definition. Okay, so as a result, essentially it depends on the problem. Okay, so depending on what you want to control, depending on what you can control, then the definition of decision variables may change accordingly.
We are producing liters orange juice. What I'm trying to ask is why don't we use liters again in the minimum average when we calculate the minimum average?
Oh, I see what you're saying. So you're talking about this part right here. Oh, I see, okay. Well, once again, so we assume that the grades are computed based on the number of oranges, okay? And number is proportional to kilogram, basically. Okay? So that's the reason why we do that. Okay? That's a good question, though. Other questions? Do I need anything else? Any other constraints on my variables? Non-negativity. Never ever forget about non-negativity. So xsi is greater than or equal to 0, xri is greater than or equal to 0, and xpi is greater than or equal to 0. So basically, if I can solve this problem, then I'm going to be able to solve the original problem. Yes? The maximum number of liters that we can produce?
We have limited number of kilograms.
Okay.
So that we have limited number of liters that we can produce from these kilograms.
Okay. All right, so the question is basically, we have only a limited number of kilograms of oranges in our stock, so that also affects our production, right? So why don't I add that as a constraint as well? So the maximum production I can have is this much. Well, the thing is, I don't need that because I already have these constraints, okay? So these constraints tell me that the values that I choose for these variables cannot be too large, and if they cannot be too large, then they all already affect my production levels, okay? So since I cannot use more than what I have, in choosing these numbers, I need to make sure that these restrictions are satisfied. And anytime I satisfy these restrictions, I can always produce, basically. Okay? So as a result, by imposing these constraints, I always make sure that the sort of number of resources that I'm going to use is not more than what I have. Okay? So based on these restrictions, I'm trying to maximize my production. Okay? If I didn't have these constraints, for instance, then that would be a problem. Okay? Other questions? All right. So This is again another example of an LP problem, or another example of a problem that can be cast as an LP problem. So now I'm going to give you one more example. Right, so this is known as short-term investment problem. And so here's a problem. So suppose that you have 10,000 liras. At the beginning of 2008, so this is a problem from last year, so that's why we have 2008, and would like to invest your money. And your goal is obviously to maximize your total amount of money at the beginning of 2011. So we assume that you have the following options. So here's the option number 1. Then here is the duration in terms of years. Then we have the overall interest rate. And then this option is available at the beginning of which years, basically. So option number 1 is a 2-year option. And the overall interest rate is 26%. And this option is available at the beginning of 2008 and 2009. Option number 2 is a 1-year option, a 1-year investment tool. The overall interest rate is 12%. And this is available at the beginning of 2008, 2009, and 2010. Option number 3 is a 3-year option. Okay. The overall interest rate is 38%. And this is available at the beginning of 2008. Finally, option number 4 is a 2-year option. And this gives you 27%. But it's only available in 2009. So essentially what we want to do is we want to come up with a sort of an investment plan so that, right now we have 10,000 Turkish liras, and at the end of 3 years we want to have the largest amount of money in our bank account, okay? And we have 4 different options. So option 1 is a 2-year option. What does that mean? So if you invest now, then you get 26% plus your original investment at the end of 2 years. So for 2 years you cannot touch your money, okay? But at the end of 2 years, you're gonna, if you invest 100 liras, then you get 126 liras, basically, okay? Option number 2 is a 1-year option. So if you invest 100 lira now, then at the end of 1 year, you get 112 liras. Option 3 is a 3-year option. So you invest your money, and then you cannot touch it until the end of 3 years. And option number 4 is a 2-year option, but it's only available not this year, but next year, depending on the problem, of course, based on the problem. Okay? So the question is, how should you invest your money so that at the end of 2011, which is like 3 years from now, you're going to have as much money as possible? Okay? Is the problem clear? So, all right, so what are the decision variables? So what can I control in this problem? So we can actually control which options we're going to invest. And we can also control how much we're going to invest in each option, basically, right? Okay. So let me actually give you a simple picture, just to make it easier. So here we have 2008, 2009, 2010, and 2011. And here I have 10,000 liras. Okay? And I'm going to define the following decision variables. So first of all, I'm going to just, instead of using 2008 and so on and so forth, I'm going to use 0 for this year. 1, 2, and 3. So that's going to make it easier. So I'm just changing my timeline. So at time 0, I have 10,000 liras. And I want to maximize my money at time 3, basically, right? So I'm going to define YIT in the following way. So this is the amount of money in Turkish liras, of course, invested in option I at the beginning of year T. So what are the possible values of I? Well, I refers to the option, so I can be 1, 2, 3, or 4. What are the possible values of T? T can be 0, or 1, or 2. T cannot be 3, because at time 3 I'll all be done. Okay? So as a result, T can be 0, 1, or 2. So how many variables do I have? 12 variables, right? Exactly. Okay. Now what I'm going to do is the following. Actually, we don't need the next variable, but I'm going to define it because it's going to make the problem easier. Okay. I'm going to define it in the following way. I'm going to define by xt. So this is the amount of money available for investment at the beginning of year T. And T again can be 0, 1, 2. I'm going to also include 3 now. So the reason why I don't need this variable is the following, because if I know my investment amounts, I can always figure these out. Okay? However, this is going to make my problem easier, my model easier, so I'm going to define this variable as well. So now we have a total of 16 decision variables, I guess, right? So 12 YITs and 4 XTs. Okay? So now I'm going to try to construct my model. Now this is a maximization problem, right? So I'm trying to maximize my money at the end of 3 years, so it's going to be a maximization problem. Now what is my objective function? So I would like to maximize the amount of money I have at the end of 3 years, right? So in other words, at time 3, I want to have the largest amount of money available. Okay? So what would be the correct expression for the objective function? Maximize x3, that's very good. Why is that? Well, because x3 is nothing but, the way I defined it, it's the money available for investment right here. Okay? And that's exactly what I want to maximize, right? So I want to maximize that amount of money. So as a result, at the end of 3 years, I want to maximize the value of x3. Does everybody see that? Okay? So this is one reason why the xt variables make the problem easier, basically. Now, what are the constraints? Well, so let's start with time 0. So how much money do I have available for investment at time 0? 10,000. So how can I write this as a constraint in terms of my decision variables? So x0 is actually equal to 10,000, right? And this is a valid LP constraint, right? So 1 times x0 plus 0 times all the other variables, I have equality equals 0, 10,000, right-hand side. Okay? All right, so now at time 0, let me just go back to my problem. What are the available options? Well, at time 0, I can invest in the first option, the second option, or the third option, right? The fourth option is not available for me. Okay? All right, so how can I write this as a constraint? Well, basically, one thing you should sort of figure out is the following. For this problem, note that option number 2 is a 1-year option, right? And it's available every year. Okay? So that means that basically I claim that I should always invest my money. I should never put some money aside. Why not? Because, well, if you put some money aside, you could actually put them in option number 2 and you would have more money eventually. Okay? So in other words, that means that whatever amount you have available for investment, you have to invest them all, basically. Okay? You have to invest all of your money. Does everybody see that? The reason for that, again, is that because there's a 1-year option which is available every year. Okay? So, you know, if somebody tells me that, well, I'm going to keep 5,000 aside, I'm not going to invest in that money, then I'm going to say, well, why don't you do it? You know, just invest in this one, and in 1 year, you're going to get 12% on your money. Okay? So essentially what I'm trying to say is the following. If this is the scenario, if these are the options I have, it's always profitable for me to invest all I have. Okay? Now, however, this is not always the case in an investment problem, because what might happen is the following, not in this problem, but there might be some other problem for which, for example, here I have a 2-year option, okay? And then here, maybe I have some other 2-year option. Then, if this 2-year option is much better for me, then I can actually wait until this time period, okay? So if in that case, it might be better for me not to invest my money in the first year, okay? However, in this case, it's not an option because in this case we have this 1-year option and the 1-year option is available every year. So rather than keeping my money idle for 1 year, I can always invest in option number 2. Is that clear? So what I'm trying to say is basically there might be other cases for which it might be better off for you to wait. Okay? But not for this problem. That's what I'm trying to say. Because essentially what I'm saying is, you know, there might be a case in which, for example, here there's a very nice investment option. Then you can just wait, basically, right, until that time, and you can invest, and you can get a lot of money over here. Okay? However, for this problem, you should always invest what you have, and we're going to try to sort of model our constraints accordingly. So as a result, in the first year, at the beginning of first year, or time 0, I have 3 options. I can invest in option 1, 2, or 3. Okay? And I have 10,000 liras available for investment. So as a result, x0 should be equal to the sum of these investments, basically, right? All right, so I can write this inequality constraint, okay? And then I'm going to put everything on the left-hand side to make it look like an LP constraint. So t will be equal to 0 in y, and I can be 1, 2, or 3, right? So I'm going to have y10 minus y20 minus y30 should be equal to 0. So this basically says that x0 is equal to what I invest in option 1, plus what I invest in option 2, plus what I invest in option 3. Okay? Now, if I go back to this table again, option number 4 is not available in 2008. Okay? So how can I express it in my model? So that corresponds to Y40. This is the amount I invest in option 4 at the beginning of 0 times 0. This has to be 0 basically, right? So this basically means that I cannot invest in option number 4 at time 0. Okay? All right, so now we just took care of the first year. In the first year, I invested whatever I had. Okay? So now I'm going to move on to 2009. So first of all, I need to figure out how much money do I have available for investment at the beginning of time 1. Okay? Well, let me just go back to this picture again, this table again. Option number 2 is a 2-year option. So that means whatever I invest here, I cannot touch that money until this time, right? So as a result, I don't have any returns from the first option. But if I look at the second option, well, the second one is a 1-year option. Okay? So whatever I invest in option number 2, I'm going to get it back. Okay? At time 1. And there's no other 1-year option, so that's the only money I'm going to have available for investment. Does everybody see that? Okay? So now I need to figure out how much money do I have for investment at time 1. So x1 will be equal to what?
1 plus 0 times y20.
Exactly. So x1, the amount of money I have available for investment at time 1, will be, whatever I invested and its interest, basically. Okay? So it's going to be 1.12 times y20. And this should be equal to 0. So this basically means that x1 is equal to 1.12 y20. Okay? Sure.
For this equation, y is equal to 0 because we calculate for other options because of the relations.
Are you talking about this? So I just explained it, right? So the reason why it's equal to 0 is because essentially there is this 1-year option. Okay? So since there's a 1-year option, there's no point in not investing my money. Okay? So, I mean, if you tell me not to invest my money, I can tell you, well, I can just invest in this rather than waiting for a year. I mean, I will always get my money at the end of 1 year in this option. Okay? So, as I tried to explain earlier, basically, in this problem, okay, that's important. In this particular example, you're always better off investing all of your money. Okay? And the reason is this option number 2. Option number 2 is a 1-year option and it's available every time. Okay? So there's no point in not investing and waiting for a year. Because whatever I invest, I will already get at the end of 1 year. Okay? So as a result, if this was 2, then you would be right. Okay? Then that would be a different story. But for this problem, you should always invest what you have. Okay? In other words, in an optimal solution, you should always invest all your money. Okay? Other questions? All right, so is this clear? So is this equation clear? Sure.
If we didn't put our money in first year, also the first option can be possible to start in the second year? Because it's a 2-year option, but if we didn't touch it in the first year, we can also start it in the second year.
Exactly. So essentially what this means is the following. In option number 1, I can actually invest my money either at time 0 or at time 1. Okay? If I invest in time 0, then I get it back over here. And if I invest in time 1, then I get it over here.
But you said we can only choose option 2 this year, so...
No, I haven't said that. So all I said was basically right now I'm just computing how much money can I invest at this point. So this is the amount of money available for investment. I haven't invested yet. Now I'm going to invest. Okay? So x1 is the amount of money available for investment at time 0. At the beginning of time 1, sorry. At the beginning of time 1, I'm going to have this much money available for investment. Okay? So now I'm going to go back and reinvest my money right here. So now I'm going to ask myself the same question. So what are my options? What are my investment options in 2009? Well, I can invest in option 1, or option 2, or option 4. Okay? So now I'll just play the same game. Since I have to invest everything I have, x1 minus, so I can invest in the first option. It's going to be y11. I can invest in the second option, so it's going to be y21. Or I can invest in the fourth option, right? So it's going to be minus y41. And this should be equal to 0. So now I'm saying that whatever I have at the beginning of year 1, I can invest in option 1, or option 2, or option 4. Okay? All right, what about option number 3? Well, option number 3 is not available in 2009, so I'm going to set it equal to 0. Okay? So basically, y31 will be equal to 0. Is that clear? So I computed whatever I have available for investment at time 1, then I'm reinvesting that money in 3 options. Okay? So now I'm going to come back to here. So now I'm at the beginning of year 2. So again, I'm going to ask myself, how much money do I have available for investment? Okay, that's going to be my x2. So how can I compute x2? Well, you have to be careful here. So at time 2, I will get money from 1-year option here, or I will get money from a 2-year option here, basically, right? So I need to actually compute that. So if I go back to my table again, I have to look for 2-year options that were available in 2008. So I have this one, and that's it. Then I have to look at 1-year options that are available in 2009. I have only this one. So I'm going to have 2 returns, basically. Okay? So what are those returns? Well, whatever I invested in option 1 at time 0 will return with a 26% interest rate. And whatever I invested in option 2 at time 1 will actually return with 12%. Okay? So I need to write them out. So x2 will be equal to what? 1.26 times y10, right? So whatever I invested in option 1 at time 0, it's going to return. And also 1.12 times, so now whatever I invested in option 2 in year 1 will also return. Okay? So it's going to be y21, right? Will be equal to 0. Is that clear? So essentially what I have at the beginning of year 2 comes from a 2-year option at the beginning of time 0 and the 1-year option at the beginning of time 1. Yes?
Or we can say 1.20 times 1.20 by 20, right?
Say again?
Instead of 1.12 by 1, we can say 1.12 square times by 20.
No, we cannot say that because essentially, you know, whatever I invested in option 2 here, I already reinvested here. Okay? So
another 1.12 times.
No. What I'm saying is the following. So at time 0, I already invested some money in 1-year option, and then I reinvested that money again. So not necessarily the same option though. I can invest it in something else. Okay? So it's not like if I don't touch that money, I'm going to get the same interest. It doesn't work that way. So I'm making a decision every year, basically. Okay? All right, so now what are the options for year 2? Investment options for year 2? Well, there's only one, which is option number 2, right? So basically, whatever I have, I should invest in that option. So x2 should be equal to the amount I'm going to invest in option 2 at the beginning of year 2, so which is y22. This should be 0. Okay? And the other options are not available at time 2. So as a result, I need to make sure that I cannot invest in them. So y12 is 0, y32 is 0, and y42 is 0. Okay? So finally, I need to figure out how much money I'm going to have at the end of year 3. So what's the value of x3? Well, okay, so the amount of money I'm going to have here comes from 1-year options in time 2, plus 2-year options in time 1, plus 3-year options in time 0. Okay? So I need to figure that out. So let's start with year 0. In year 0, I may have invested some money here. I'm going to get it back. Okay? With a 38% rate. So it's going to be 1.38 times Y31. Y30, thank you. Okay, then I should look at 2-year options in time 1. What are the 2-year options in time 1? So I have this one, the first one, and I have the fourth one as well. Okay, so the first one will come back with 26%, and the fourth one will come back with 27%. Okay, so what do I have? I have 1.26 times, I'm investing in the first option at the beginning of year 1, minus 1.27 times Y41, basically. Okay? So once again, I'm receiving the interest from this one and the interest from this one as well. Okay? And finally, I should look at 1-year options at time 2. So the only option at time 2 was basically option number 2. And that brings 12%. So it's going to be minus 1.12 times Y22. And that should be equal to 0. So essentially this says that X3 is equal to what I have from 3-year investments 3 years ago, plus what I have from 2-year investments 2 years ago, plus what I have from 1-year investments last year. And if I add them up, that's going to be my total return. Anything else? Any other constraints? Non-negativity, you should never forget. So for all values of t, and also yit should be non-negative. So for all I and j, I and t. And if you solve this problem, then you're going to have the best investment decision, basically, okay? Any questions about this? So once again, I mean, let me just... this is going to take just 1 minute. So it looks complicated, but it's actually pretty straightforward, okay? So essentially, at the beginning of each year, we're first computing how much money we have available for investment, okay? And then we're saying that that money should be invested, should be reinvested in the options. So each of the constraints is in that form. So first I compute how much money I have for investment, then how am I going to invest my money in different options, okay? And I do this at the beginning of year 0, year 1, year 2, and year 3. And year 3 actually gives me what I want. Okay, by maximizing that, I'm actually maximizing my total return. Okay, so I'll see you next Thursday.